Welcome to the Notes on Optimization for Damani Ranch High School. We're going to be looking at problems where we are asked to find an optimal solution that would benefit somebody. So maybe something that would be cost effective or something like that would create a biggest product, something like that. So here's our first example. A farmer has 2,400 feet of fencing. He wants to fence off a rectangular field that borders a straight river. So he does not need a fence along the river. We want to find the dimensions of the field that have the largest area. I'm going to start by drawing a picture of what's happening. So we've got some river that's straight. And we have a rectangular field that has one of its boundaries is the river. It's an awesome rectangle. We'll try again. Okay, and this is a rectangle. And so something we could do is we could put in some variables here. We want to find the dimensions of this field. And so I can call some of these dimensions x and some y. For this rectangle. And then they mention a couple different things. They mention the fence that we have to make. And we also want it to be a largest area, the largest possible area. So what we'd like to find the max of is we want to find the max area. And so one of the formulas I will need to use is the area of a rectangle, which is base times height, or x times y. However, we also have what we call a constraint. We have like a limited amount of fencing that we can use. So this puts a restriction upon how big we can make this field. Now the fencing is really only being used on 3 sides right here. So the amount of fence we're using is very similar to the idea of a perimeter. In fact, I often call it perimeter. But the perimeter is only going to be using 3 sides instead of the 4 because we're not building a fence along our beautiful little river that's happening right here. So my constraint is that my perimeter that I can use, which will be made up of 2 x's and 1 y, by the way, I chose to name the variables, and that perimeter is 2,400. So I want to use that 2,400, but I don't want to use more than that. Now, the way we find maximums in general, when we're looking at calculus, is we are going to be looking at derivatives. And so if we find our derivative, we could find a critical value. We could verify that something is a max or a min by looking at the concavity of the function. And so that's really what we would like to do. So we'd like to find a derivative here of the function that I want to maximize. So I am going to find a derivative here. And the reason I'm choosing to find the derivative of a is because this is the one that I want to maximize or want to optimize. Sometimes that could be a max or it could be a min. Just depends on the situation, but we want it to be the most possible desirable answer. So I want to find a derivative of this, which will allow me to find critical values where I might have an extrema. But I don't love here that in this problem that I've got both an x and a y, because this is, if I'm taking a derivative on that right-hand side, I'd have to use product rule. If I have the opportunity to avoid that, I will. In fact, I do have the opportunity to do that because I have this constraint over here that came from my kind of funny little fakey perimeter here. And so what I'm going to do is I'm just going to isolate one of my variables. I could choose to isolate x or y, but I think that isolating y seems pretty easy. And then what I can do is I can replace y and just substitute in and rewrite the area in a little bit more friendly form as x times 2,400 minus 2x. And you could use product rule here, but I'm just going to distribute because I find that to be faster. And now I'll find my derivative. So a prime is 2,400 minus 4x. Now what I'd like to do when I'm finding the derivative is the whole point of finding the derivative is I want to set that derivative equal to 0 and solve for my critical values. So solve for, in this case, x, could be y, whatever. And so in this problem, I'll set this equal to 0 and use a little factoring. Or you could have just moved terms over, up to you. But it looks like x is 600. This is my critical value. Or my critical point, however you want to describe it. So this is the place where I might have a relative extrema. Now, if I want to find out and verify that this is a relative extrema, I can do this in a lot of ways. One of the ways I could do this is by setting up an alt table and looking for sign changes. I find that that works great in many contexts, but it's also very easy to then use the second derivative test and find the second derivative and evaluate that at whatever the critical value is that we found. And this will help me decide what the concavity of A is, the concavity of the area, and that will tell me what type of extrema I have. So the second derivative of X, or of A here, would end up being, looks like just -4. There's actually no need to evaluate it because this second derivative will always be a negative, which tells me that A is concave down. And this one's actually concave down everywhere. Some will only be concave down in certain instances, but this one's concave down everywhere, which means my relative extrema, or my critical value of 400, is going to be a max. And in fact, since this is concave down anywhere, that is the only max. So it is truly the maximum, the place where we will have the maximum location. So what I'm trying to do is find the dimensions. Well, the dimensions are both X and Y. I now know what X is. This would be 400 feet. And keep in mind, we had 2,400 feet that we could use here. So in my whole thing. Now the X is going to be used twice. So I could plug this in right here to find Y. Y would be 2,400 minus twice 400. So it turns out that Y is 1,600 feet. So 2,400 by 1,600 feet would give me the most area possible. What was that? 640,000 feet something, square feet. And that will give me my maximum. So this kind of method here of setting up a constraint, finding out what function I'm trying to maximize, doing a derivative and finding critical values, and then examining the second derivative to look at the concavity to decide what type of, you do need to verify that this really is going to provide the right type of extrema. All right, let's take a look at another very common problem. We have a piece of cardboard. It's 14 inches by 10 inches. Initially, it's going to be cut up, but it starts off 14 inches by 10 inches. And what we're going to do is we are going to cut out the corners and remove them. So these corners will be removed right in here. And when they are cut out and removed, we're then going to, along these dotted lines, we're going to then fold up the cardboard along these like little dotted lines here. And it'll form this open box. We want to determine the height of the box that will give a maximum volume. The height of the box that will give the maximum volume. Okay, so the item that I'm trying to maximize is the volume. So I want to try to find the max volume. And the way you find the volume of a prism, which is what this box is length times width times height. Now you might notice I'm not going to use length times width times height. They gave us a little hint here, is that we could call the height, which is where we're going to be folding up, H. And that H is being removed on both sides as we cut out these boxes or these squares in the corners. So along this length of 14, I had to remove H twice, which is why the length here of this prism is 14 minus 2H. The height is H because that's when it would fold up. And then in a similar fashion, I started off with 10 inches along the side of this cardboard, but I cut out H twice when I cut out those squares to fold up the box. So this is my length and width and height. So H, so the volume can be found by H times 10 minus 2H times 14 minus 2H. You might notice on this one, we only have one variable on the right-hand side, which is great. And what's happening here is there are constraints in this problem, but we've kind of already dealt with them. What the constraints are the 10 by 14. And so by renaming the length and the width and the height in terms of the 10 by 14 with those H's removed, We've actually dealt with the constraints already, so this is a little bit different than example one. I am going to want to find a derivative of this, but to me it's worth it to just expand this out first. I'm just going to expand out, just multiply these two binomials. We'll see if I can do it correctly. So 140, I have minus 20h and minus 28h, which if I'm doing my math right, we'll see is minus 48h, and then plus 4h squared. And now I'll distribute the h. Okay, so I'm going to be finding a max, kind of I wanted to find out what I'm going to try to optimize. So I need some type of function to optimize. In this case, it's the volume. And I want to then find the derivative of that volume. So I will use power rule here to get V prime is 140 minus 96h plus 12h squared. And then what I'm going to do from here is I'm going to set this equal to 0 and solve for critical values. In this case, it's for h. All right, so we're going to set this derivative equal to 0 and solve. And looking at this, I'll reorder it. I don't believe this factors. So you could use the quadratic formula here. I'm not going to go through all the math of that. But if you go through the quadratic formula, I used a calculator and found out that h is either 1.198 or h could be 6.082. Now, sometimes both of those won't make sense in the problem. Keep in mind that this side right here is 10 minus twice h. So if h is 6.082 and I have to subtract that twice from 10, that's 10 minus a little over 12. I would end up with a negative side length. So this one's not going to make sense right here. I'm going to reject that value for h. So thinking this might be the value of the height that gives the max volume. Just to verify that though, once I have solved for those critical values, I'm going to examine the second derivative. I'll evaluate it at the critical value that I found, and the sign of that will tell me about the concavity of V. And I will use that to just verify that this is giving me the absolute max. All right, so the second derivative of V, let's see, would be negative, let's see, negative 96 plus 24h. And if I evaluate that when h is 1.1918, let's see, I'm going to still get a negative. I actually don't care what the value is. What I care about is that this is still going to be a negative. What this tells me is that V is concave down, at least at that point. It doesn't mean that this is concave down everywhere. This could end up being positives for certain values of h, but it is concave down at the one point at h is equal to 1.1918. So at that instant, I do have a max right here. And because this is my only critical value, remember the other critical value didn't make sense in the context of the problem. So because this is the only critical value that would work, h must be something, I guess, less than 5. Otherwise, we would get negatives in here for my width here. What this tells me is that I will always end up with this as the highest max. I'm never going to have another turning point where I could then rise back up again. So since this is the only critical value, this is an absolute max. And so the height that gives the maximum value is 1.1918, and I guess this is measured in inches according to the original problem. Here's another one. 600 square meter plot of land. So this is already an area value right here. is to be enclosed by a fence, and it's going to be divided into two equal parts by another fence parallel to one pair of the sides. This is going to be a rectangle. So even though the units for area are square meters, that does not mean that this is a square. We have other information at the end that this is a rectangle. So I've got some plot of land. The area of this is 600. And what we're going to do is we're going to enclose this by a fence, and then we're going to divide this by another fence parallel to one of the pair of sides. Maybe this other one is going straight up and down. Maybe it's going sideways. I don't know, but it will split it into two equal parts. I'll choose to make it go this way. It would work out the same if I did that as a horizontal split. But what's going to happen is that's going to split these horizontal pieces the same way because this should divide into two equal parts. I'll call these both y. We want to minimize the amount of fence used. Well, to minimize, the function that we are minimizing here is the fence, which is on the outside. I guess that's another y. And there's also this fence inside. So the perimeter here of this fence is formed by 4 x's and 3 y's. That's how my fence is built. Going back to my area, the area is 600, and that is formed by this full length on the bottom, which is 2x times y. 2x times y. Now, the one I want to minimize is the perimeter. So I am going to want to take the derivative of p, but I don't like that I have both an x and a y. So I'm going to use this constraint that I only have a certain amount of area to work with, and I'll use the constraint to change one of my variables. I can do this a lot of different ways, but maybe I'll solve for y. It doesn't actually matter. So y would then be equal to 600 divided by 2x, which is 300 divided by x. So I'm going to go to my perimeter, and I will rewrite y as 300 over x. Now I am going to want to find the derivative of this, and so I think this would be easiest to find if I use x as a negative with a negative power. So p prime is 4 minus 900 times x to the power of negative 2. After I find this derivative of p, I then want to set that equal to 0 to find the critical values. In this case, I'm solving for x. So I will set this equal to 0. And maybe I'll just do some reordering and move this around. So this would be 900 over x squared is equal to 4. Lots of ways to solve this. I'll choose to cross multiply and get 4x squared is 900. So then x squared is 900 over 4. And x is, when I square root both sides, let's see, the square root of 900 is 10 root 3 over 2. Now, technically, this is a plus or minus 10 root 3 over 2. However, we're talking about measurements, and measurements are positive. And, you know, depending on the situation, quite honestly, it's quite common for these to be used as decimals in these problems. They don't have to be, but I'll rewrite this maybe as a decimal at the end if I want. Okay, but x is 10 root 3 over 2. I do need to verify that this is truly a minimum. So to do that, I'm going to go ahead and find the second derivative, and I'll evaluate it at the critical value I just found. So let's see, the second derivative of p would be, if I use power rule here, 1800 over x cubed. So if I evaluate that at 10 root 3 over 2, oh, I guess this would be over x cubed. Sorry, that's a power of negative 3. This would be 1800 over 10 root 3 over 2 squared or cubed. And that's just a positive. All I care about is that a positive. What this tells me is that p is concave up, at least at that moment, at the instance where x is this value. Oh, hello. 10 root 3 over 2. I guess I can divide that. 5 root 3. I'm super funny. There we go. And really, I mean, actually, this is going to be concave up anywhere x is positive. So it would actually be concave up anywhere, but I could write it this way if I'd like. What this is telling me is that indeed my critical value will be a minimum here for this region. So I am finding what I wanted, but I want both dimensions, both the x and the y. So for my dimensions, which is the final answer, I've got that x is 5 root 3 and y is supposed to be, oh, would be in meters. And y is 300 divided by that, which would be 60 over root 3, which rationalizes to 60 root 3 over 3 or 20 root 3. And actually, that's not quite right. That is true for y, but x is 5 root 3 and x is not the whole dimension. The whole dimension for this is 2x. So let's make that 10 root 3. If I verify that, this should multiply to an area of 600, and it does, which is, by the way, how I found my error, because I realized that does not multiply out correctly, and it should to meet that constraint. All right, on to the next one, example 4. A rectangle has its base on the x-axis. Two upper vertices are on this parabola, and we want to find the maximum area of the rectangle. All right, what? Rectangle. All right. So I've got this coordinate system. I have a parabola. I know that the vertex of the parabola is at 12, 0, and it's opening down, so looks like this-ish. It's a height of 12. All right, I have a rectangle. Its base is on the x-axis, and the upper vertices are on the parabola. Upper vertices are on the parabola. So wherever this vertex is, this is an x, y point here. This would be a negative x, y point here on that one. All right, so this is x here and here, just going in different directions. And then the height of the rectangle is y. We want to find the maximum area of the rectangle. So what I'd like to maximize, I want to maximize the area, which is length of 2x times the height of y. My constraint is my parabola. This tells me the relationship between x and y that I have to make sure stays true. 12 minus x squared is another way to describe y. So because I am going to need to take a derivative of whatever I'm optimizing, max or min, I don't love the two variables over here, so I'm going to replace y with what it's equal to, which is 12 minus x squared. I'll distribute this. My area could be rewritten as 24x minus 2x cubed. So if I find the derivative of this, 24 minus 6x squared, I will then set this equal to 0 and solve for critical values. Oops. Let's see if I can factor. I'll take out the GCF of 6 and factor that as x, or 2 minus x and 2 plus x. So x is either positive or negative 2. Now we're describing x as a length, so we're going to use the positive 2. And I'll now examine the second derivative here. And the second derivative would end up being negative 12x. And if I evaluate that second derivative at my critical value of 2, I will get a negative 24, which is telling me is that A is concave down at x is equal to 2. This is also the only critical value here that makes sense in the context of the problem. So we are safe to say this is an absolute max here. So x is going to equal 2. We can verify that with our concavity. To find the max area, as a reminder, area is 2 times x times y. So that would be 2 times 2 for x. And then to find y, I can go ahead and plug in a 2. So this would be 12 minus 4, which is 8. And my max area here is 32 square units. They didn't give me any units, so I could just write 32 if I want. All right, last problem. A window is being built. The bottom is a rectangle. The top is a semicircle. There is 12 meters of framing materials that we're going to use. That frame is on the outside. Just to clarify, that dotted right here is just to help me see where the semicircle kind of splits up. But that's not actually part of the framing of the window. Just on the outside is the frame. Let's see. So I'm going to use 12 meters of framing, and I need to find the height of the rectangular portion to let in the most light. Which means I'm trying to find a maximum, but you might wonder, what am I finding the max of? To let in the most light, I need the most area. So I need to find the max area of this window. And this is a composite shape. This window is formed by two things. Part of this window is a rectangle, which would be length times width, in this case, 2r times h, or 2rh. And then I have this semicircle here. In other words, I have half of the circumference of a circle. That is awesome. I have half the circumference of a circle. Not much better. Remember, circumference is 2 pi r. And so if I want half of that, I just want pi r. And we're using r, the radius, just as r, because it is an unknown quantity. So this is the area I need to maximize. Again, I might notice, I've got both an r and an h, which is not very much fun. And so I need to start thinking about a constraint because I have more than one variable. And I do have a constraint. The constraint that I have is I only have 12 meters of constraint. Wow, I keep spelling constraint wrong. I'm just realizing there's only 12 meters of framing materials. So I have to make sure that my perimeter here stays at 12. Or that's the most I can use. So I would use an H, a 2R, and another H. Ooh, this area is wrong. That is not area. Area of a circle is pi r squared, and I want half of that. There we go. We're going to try this again. Doing awesome today. All right, the perimeter for this guy. For the rectangular portion, I'm using 3 sides, which would be H twice, and then the 2R at the bottom. And then the circumference of that entire circle is 2 pi r, but I only want to go around half of the circle since it's a semicircle, so plus pi r. And that perimeter is 12 at the most. So looking at what I want to maximize, which is my area, what I really don't like is this h, because everything else on the right-hand side is in terms of r. So I'm going to actually solve for h in my constraint, and then I will use that to replace h. So 12 minus twice r and minus the pi r is 2h. So then 6 minus r minus pi r over 2 is what we could use as h in this problem. So if I rewrite my area in terms of one variable instead of 2, that would be that the area is 2 times r times 6 minus r minus pi r over 2 plus the half area of a circle, or the area of a semicircle. So if I distribute here, I have 12r minus 2r squared minus, let's see, the 2's cancel out, so pi r squared plus 1/2 pi r squared. Just double checking because I have made a large number of errors on this video, so I'm trying to see if I can verify this before I move on. I've got some like terms here that I'm just going to continue to do just a little bit of simplifying before I take my derivative. So let's see, this would be minus 1/2 pi r squared. And now I will find the derivative of a, which is 12 minus 4r minus pi r. And I would like to set that equal to 0 and solve this. So I want to solve this for r. If I remember correctly, this one kind of starts to make the most sense potentially as a decimal. Although we could solve it without, I could move the 4 r and the pi r over to the other side and change their signs. Factor out an r. And so r is 12 over 4 plus 5 pi. It just kind of feels a little bit like that's hard for people to tell what that is. So maybe I'll just convert that really quickly to a decimal. This is approximately 1.6803-ish. Now what we're trying to find is we're trying to find h. But before we do that, let me just verify that r would give me a maximum. So to verify that r will give me a maximum, I am going to look at the second derivative, which would be negative 4 minus pi. And notice there's not anywhere to even plug in an r because this was linear. So negative 4 minus pi is always negative. So what this is telling me is that a is always concave down. And since a is always concave down, r would then have to be a max. And since it's my only critical value, it must be an absolute max. So I must have the right value for r to provide the max area, but I want to find h. So to find h, I will do 6 minus r. I'll probably use the exact value, since I'll just put this into the calculator. Minus pi times this nonsense. And this will tell me what h is. And I am getting, oddly enough, the same answer for h as I did for 2r. So this must have to end up being a square in order to have the maximum area here on this one. And I think this is in meters. Oops, I lost a digit. Try again. All right, and that is the end of this video for optimization notes.